Instruction sets, addressing modes and formats, Computer Science 410, Chapter 13, Part 1. We're going to take this one in two goes. It definitely puts less stress on the recording software, my cognitive burden, and on the rendering. So we'll do this in two parts, Part 1 and Part 2. So in Chapter 12 we focused on what an instruction set does. We examined the types of operands and operations that can be specified by machine instructions. This chapter will look at how to specify the operands and the operations for these instructions. Two issues. One is how is the address of an operand specified, and the second is how are the bits of an instruction organized to define the operand addresses and operation of that instruction. So with that in mind, let's get into addressing modes. This is chapter 13.1. So the address field or fields in a typical instruction format are relatively small. We'd like to be able to reference a large range of locations in main memory or, for some systems, virtual memory. To achieve this objective, a variety of addressing techniques have been employed both in the past and the present. Immediate, direct, indirect, register, register input, displacement, and stack. We'll take a look at all of these over the course of this lecture. They all involve some trade-off between address range and or addressing flexibility on one hand, and the number of memory references in the instruction and the complexity of the address calculation on the other hand. So this is a nice graphic of how the various addressing modes work, and is figure 13.1 in the 10th edition of the text. In the next several slides, we're going to examine each one of these individual, but here they are all pictured, and if you get a chance to refer back to this in your textbook, it's definitely worth looking at as you go through the material. But let's start with immediate addressing. So immediate addressing, this is the simplest form of addressing. Basically the operand is equal to an address. This mode can be used to define and use constants or set initial values of variables. Typically the number would be stored in 2's complement form. The leftmost bit of the operand field is used as a sign bit. So this is nice because no memory reference other than the instruction fetch is required to obtain the operand. So you save one memory or cache cycle in the instruction cycle. The disadvantage is the size of the number is restricted to the size of the address field in the instructions, which in most instruction sets is pretty small compared with the word length. The next form is direct addressing. And this is a very simple form of addressing in which the address field contains the effective address of the operand. So this technique was common in earlier generations of computers, but it's not common on contemporary architectures. It requires only one memory reference and no special calculations. The obvious limitation is that it only provides a limited address space. So let's talk about a more complicated one in the form of indirect addressing. With direct addressing, the length of the address field is usually less than the word length, thus limiting the address range. So one solution is to have the address field refer to the address of a word in memory, which in turn contains the full-length address of the operand. That's known as indirect addressing. So here the effective address is an address that has the word memory, which contains the full-length address of the operand. The parentheses are to be interpreted as meaning the contents of the address here. The obvious advantage of this approach is that for word length of n, an address space of 2 raised to the n is now available. The disadvantage is that the instruction execution requires 2 memory references to fetch the operand, one to get its address and a second to get its value. Although the number of words that can be addressed is now equal to 2 raised to the n, the number of different effective addresses that may be referenced at any one time is limited to 2 to the k, where k is the length of the address field. Typically that's not a burdensome restriction, and it can actually be an asset. In a virtual memory environment, all the effective address locations can be confined to page 0 of any process. Because the address field of an instruction is small, it will naturally produce low number direct addresses, which would appear in page 0. The only restriction is that the page size must be greater than or equal to 2k. So when a process is active, there will be repeated references to page 0, causing it to remain in real memory. So indirect memory references will involve at most one page fault rather than 2. A rarely used variant of this, and you can look it up on page 460 of the text, is multi-level or cascaded indirect referencing. The disadvantage there is that 3 or more memory references could be required to fetch an operand. Not all the time, but it could work out that way. So that one's kind of a footnote. Another technique is register addressing. Here the address field refers to a register rather than a main memory address. Advantages: only a small address field is needed in the instruction. There's no time-consuming memory references that you need to do. The disadvantages are the address space is pretty limited, registers are not available for other tasks, and it places a burden on the program or compiler writer. So if register addressing is heavily used in an instruction set, this implies the processor registers will be heavily used. Because of the severely limited number of registers compared with main memory locations, their use in this fashion makes sense only if you're employing them efficiently. If every operand is brought in to register from main memory, operated on once and then returned back to main memory, then you've got all these wasted intermediate steps. If instead the operand in the register remains in use for multiple operations, then you get the savings. An example of this is an intermediate result in a calculation. In particular, suppose an algorithm for 2's complement multiplication were to be implemented in the software. The location labeled A in the flowchart is referenced many times and should be implemented in the register rather than in a main memory location. Register indirect addressing is analogous to indirect addressing. The only difference is whether the address field refers to a memory location or a register. So the effective address is the contents of the register. The advantages and limitations of this are basically the same for indirect addressing. In both cases, the address space limitation, limited number of addresses, or range of addresses, so the address field is overcome by having that field refer to a word length location containing an address. In addition, register indirect addressing uses one less memory reference than indirect addressing. Displacement addressing combines the capabilities of direct addressing and register indirect addressing. So the effective address is equal to the address plus the register. Requires that the contents of the register. Requires that the instruction have 2 address fields, at least one of which is explicit. The value contained in one address field, value is equal to A, is used directly. The other field refers to a register whose contents are added to A in order to produce the effective address. Most common uses of this technique are relative addressing, base register addressing, and indexing. Relative addressing, this is also called program counter relative addressing. The implicitly referenced register in this case is the program counter, also known or abbreviated as the PC. The next instruction address is added to the address field to produce the effective address. Typically the address field is treated as 2's complement number, and the effective address is a displacement relative to the address of the instructions. This one exploits the principle of locality, which we talked about at great length. If most of the memory references are relatively near to the instruction being executed, then the use of relative addressing saves address bits in the instruction. Base register addressing. Here the reference register contains a main memory address, and the address field contains a displacement from that address. The register reference may be explicit or implicit. Exploits locality memory references, and it's a convenient means of implementing segmentation for memory. In some implementations, a single segment base register is employed and used implicitly. In others, the programmer may choose a register to hold the base address of a segment, and the instruction must reference it explicitly. For indexing, the interpretation is typically the following. The address field references the main memory address, and the reference register contains a positive displacement from that address. Note that this usage is just the opposite of the interpretation of base register addressing. Of course, it's more than just a matter of user interpretation, because the address field is considered to be a memory address in indexing. It generally contains more bits than an address field in comparable base register instruction. Also, we shall see that there are some refinements to indexing that would not be useful in the base register context. Nonetheless, the method of calculating the effective address is the same for both base register addressing and indexing. In both cases, the reference register reference is sometimes explicit and sometimes implicit. You can also do this as pre-index, post-index, or auto-index. Next is stack addressing. A stack is a linear array of locations, sometimes referred to as a push-down list or last in, first out queue. That seems kind of weird. A stack is a reserved block of locations. Items are appended to the top of the stack so that the block is partially filled. Associated with the stack is a pointer whose value is the address on the top of the stack. So, just like you do with data structures, you have the pointer to the top. Stack pointer is maintained in the register, and references to stack locations in memory are in fact register indirect addresses. It's a form of implied addressing. The machine instructions need not include a memory reference, but implicitly operate on the top of the stack. So here's a nice summary. This is, I believe, table 13.1 in the 10th edition of the text. It gives you the different modes, the algorithms for them in terms of finding either the address or the contents of the address. If you're looking up a full address from a word, and such as indirect addressing, the advantages and disadvantages. And that'll be part of the homework, is defining each one of these. So you'll get a chance to work with these a little bit more. So with that in mind, let's look at X86 and ARM addressing modes, and this corresponds to chapter 10.2. And as you might surmise, it gets a bit detailed. I'm going to try to keep it as straightforward as possible for you. So X86 addressing modes, it's complicated, as you might expect. The X86 address translation mechanism produces an address called a virtual or effective address that is offset into a segment. The sum of the starting address of the segment and the effective address produces a linear address. If you're using paging, this linear address must pass through a page translation mechanism to produce a physical address. So table 13.2, this is on page 465 of the 10th edition, lists the X86 addressing modes. And you can see you have quite a wide variety of options available at your disposal. For immediate mode, the operand is included in the instruction, just like we talked about earlier. It can be a byte, word, or double word of data. For register operand mode, the operand is located in the register. For general instructions such as data transfer, arithmetic, and logical instructions, the operand can be one of the 32-bit general registers, one of the 16-bit general registers, or one of the 8-bit general registers. There are also some instructions that reference the segment selector registers. The remaining addressing modes reference locations in memory. The memory location must be specified in terms of the segment containing the location and the offset from the beginning of the segment. In some cases, the segment is specified explicitly. In others, the segment is specified by the simple rules assigned a segment by default. So in displacement mode, the operand's offset is contained as part of the instruction as an 8, 16, or 32-bit displacement. With segmentation, all addresses and instructions refer to an offset in the segment. The displacement addressing mode is found on few machines, as mentioned earlier, because it leads to these really long instructions. In the case of the X86, the displacement value can be as long as 32-bit, making a 6-byte instruction. That's quite large. Displacement addressing can be useful for referencing global variables. So I guess you probably do need those in things like assembly language, but not so much in higher level languages. The remaining addressing modes are indirect. So basically everything after displacement, base with displacement, those are all indirect. Base mode specifies that one of the registers contains the effective address. This is equivalent to what we called register indirect addressing. Base with displacement mode, the instruction includes a displacement to be used as a base register, which may be any of the general purpose registers. Scaled index with displacement mode, the instruction includes a displacement to be added to the register, in this case called the index register. The index register can be any of the general purpose registers. There is one that's reserved, it's called ESP, which is generally used for the stack processing, so you can't use that one. In calculating the effective address, the contents of the index register are multiplied by a scaling factor of 1, 2, 4, or 8, and then added to a displacement. This one's pretty convenient for indexing arrays. A scaling factor of 2 can be used for an array of 16-bit integers. 4 could be used for 32-bit or floats. And finally, a scaling factor of 8 could be used for doubles. Base with index and displacement mode sums the contents of the base register, index register, and displacement to form the effective address. Again, the base register can be any of the general purpose registers, and the index register can be any general purpose register except that one called ESP, which points to the stack. As an example, this addressing mode could be used for accessing a local array on a stack frame. Can also be used for processing two-dimensional arrays. The base scaled index with displacement mode sums the contents of the index register multiplied by a scaling factor, contents of the base register, and displacement. This is useful if an array is stored in a stack frame. In this case, the array element would be 248 bytes in length. This mode also provides efficient indexing for a two-dimensional array when the array elements are 248 bytes in length. And last but not least, relative addressing. This can be used in transfer control instructions, your jump less than, jump greater than, go-to instructions. The displacement is added to the value of the program counter, which points to the next instruction. In this case, the displacement is treated as a signed byte, word, or double word value, and that value either increases or decreases the address in the program counter. So, with the X86 done, let's take a look at ARM. So, ARM indexing instructions, you can load and store instructions. The load and store instructions are the only instructions of reference memory. This is always done indirectly through a base register plus an offset. There are three alternatives with respect to indexing. One is offset. For this mode, indexing isn't used. An offset value is added to or subtracted from the value in the base register to form the memory address. Pre-index, the memory address is formed in the same way as for offset addressing. The memory address is also written back to the base register. In other words, the base register value is incremented or decremented by the offset value. And then post-index, the memory address is the base register value. An offset is added to or subtracted from the base register value, and the result is written back to the base register. So for data processing instruction and branch instructions that are different than load and store, for data processing, use either register addressing or a mixture of register and intermediate addressing. For register addressing, the value in one of the register operands can be scaled using one of the 5 shift operators. For branch instructions, the only form that you're allowed is immediate. Instruction contains a 24-bit value. It's shifted 2 bits left, so the address is on a word boundary, and the effective range is plus or minus 32 megabytes from the program counter, which is where we get that limitation when we're using the ARM architecture. It also has the capability to load and store multiple addresses. Load multiple instructions load a subset, possibly all of the general purpose registers for memory. Store multiple, store a subset, and possibly all of the general purpose registers to memory. The list of registers for the load or store is specified in the 16-bit field in the instruction, with each bit corresponding to one of the 16 registers. Load and store multiple addressing modes produce a sequential range of memory addresses, as you might expect, for where we're going to load or store them from. So next time we'll look at instruction formats, talk about X86 and ARM instruction formats, and there's about 3 to 4 pages where they discuss the general principles of assembly language and why assembly language is such an improvement over machine language. Thanks for listening.